Hello everyone, hopefully you're doing well. In this video, we're going to continue with chapter 9, modeling our world. These sections would focus on linear modeling, so we call it Unit 9B. In Unit 9A, we represent functions with tables and graphs and tells you that we can use also formulas to for functions. We now turn our attention to a more common and versatile way of representing functions with equations, right? Although equations are more abstract than pictures, they are easier to manipulate mathematically and give us greater power when creating and analyzing mathematical models. Huh? We can understand the basic principle of mathematics, mathematical modeling, by focusing on the simplest models, like linear models, right? Which can be represented by a linear function. So usually, anytime we said we have a linear function, is a function that can rewrite in the form ax plus b. Or if you want to use y, you can write it ax plus b. Or there is in different ways you can write it mx plus b. Or there is this one can be also linear, ax plus by equals c. Those are all examples of linear functions, right? Those are linear functions. They are linear functions because they don't have any exponent greater than one. So x is power one, y is power one, etc. So remember, in functions like this, a, b, and c are all constants, are all real number, are all constants. So they are just numbers, only x and y are variables. So, but it's all real numbers in this case. All right. So most of all, that's what's gonna happen. I would say that linear functions are, as we said, that's what we understand the basic principles of mathematical modeling by focusing on the simplest models, linear functions, which can be represented by linear functions, which graph as a straight line. So if they ask you to graph a function's graph y equal 2x minus 1, a graph like this, you need the XY plane you learned about in the previous sections. Remember, the horizontal axis is X, the vertical axis is Y. So all you need to do is to find some points using coordinate of X and Y. Let's suppose you can take any. It's any. If you said X is 0, so in this particular y equal to x. If x is 0, we're going to have y equal 2 times 0 minus 1. Y would be 0 minus 1. Y would be negative 1. So you have a point 0, negative 1. Because it's a linear function. Linear. Linear means it would be a straight line. All you need to graph a straight line would be 2 points. So if I said, what if x equal 1? So let's see. If x equal 1, we're going to have y equal 2 times 1 minus 1. Y would be 2 minus 1. Then y would be 1. So we know when x is 1, y would be 1. And if you try to plot these 2 points, when x is 0, y is negative 1. So let's suppose negative 1 is here. That's our first point. This point right here would be 0, negative 1. Now, another point, we're going to try to find another point. When x is 1, y is also 1. So you see we have 1, 1. This is the second point, 1, 1. Because it's a linear functions, so we can connect these dots and continue indefinitely on both directions, and that would be the graph of y equal to x minus 1. So you see, to graph a linear function, there is no curve, there is no turning point, there is no vertex. So the only thing you're going to see is a straight line, and you only need 2 points to graph a function like this. So as you can see, set of functions, there is, the domain and the range are all real numbers. We're not only using the positive side of it, but let's suppose we go with a model, linear modeling about populations, right? Maybe about age. We'd never reach the negative side. Probably next times we remodel something, we're gonna use only the positive and the negative side of X and Y. So it all depends on what we do, but we know the negative side also exists, but we don't have. We already know some functions. I mean, some data would never be negative. If we're talking about age of students attending college, our college, we know there would be no age negatives, right? So that's why we said it's not in all models in terms of we're gonna see this. So imagine, now we're gonna talk about linear functions. So imagine that rain falls at a constant rate for 6 hours, and we use a rain gauge to measure the depth of rain accumulating during this period of time. So what we can describe as the rain depth change by using time as the independent variable and rain depth by the dependent variable. So we can graph something like this one, right? If that's ever happened. So remember, if we do that, then we're gonna graph dependent and independent variables. But let's focus on linear function as a constant rate of change and a straight line graph. So it's very important to see it that way. Um, this graph right there, you see here, what it shows that the depth, you know, um, no, that's not the graph I wanted to show you because I have multiple graphs, unfortunately. But that's not the exact one. But let's talk about mostly the rate of change because we can say that rate of change, with respect to time, we can verify it. Rate of change constant, all right? We said the rate of change is equal to the slope of the depth. So, slope is another ways of saying it. Once you graph multiple functions, if I ask you to graph f of x equal x plus 2, a very simple functions. Again, you need to construct your xy plane. Now, you can construct a small table with the two coordinate x and y. If x is 0, plug it here, f of 0, x is 0, we're going to have y equal to. So we have 1 point that is 0, 2. If x is 1, y would be 3. So we have another point. You can choose any other points. I chose these. When x is 0, y is 1 and 2. So I know that I have 1 point here. When x is 1, y is 3. See? So connect those dots and we can graph indefinitely, continue this line indefinitely. That would be our graph for the function f of x, x plus 2. Now, you see, this line is not exactly straight vertically or horizontally. It's like a slant. So there is some change in the variables of x and the variables of y that create that slant, that's diagonal. So this change, we call it slope. So that slope, we also call it the rate of change, okay? Photograph. So the greater the rate of change, the deeper is the slope. So to calculate the rate of change by finding the slope between any 2 points, we said rate of change is equal to the slope. That means change in y over change in x. In some ways, we said slope usually, slope we call it m. That means it's a change on the y values over the change on the x values. So if you have for 2 points, for a line passing through 2 points, that would be your slope, right? So we're gonna go very quick about slopes and probably um, introduce you to some other problems. Let me try to include the tables right there. Slope of a line, as we said, for when you have an XY plane, suppose this is an XY plane, right? Very straight line. This is Y and this is X, both sides, right? So any times for 2 points for a line passing through the point, I mean, these 2 points, because I don't know them yet, I can call them X1, Y1, and X2, Y2. The slope M of the line is given by the formula M equal Y2 minus Y1 over X2 minus X1. So this is the definitions. A brief definitions, but we have plenty of them. So what we mean by that, remember, if I know a value of X1, if I plug it in the functions, I'm going to find the Y1. So probably they already give you. So if I call this point right here, X1, Y1, and for another point, uh, with two coordinates, X2 and probably Y2. Now we have a second point, and let's call this coordinate, this point Y2, X2 and Y2. When you connect these 2 points, so this is the change. You see the change between these 2 points. We're gonna call them change in X and change in Y. So if you graph between these 2 points, as you can see, there is a change in those numbers. So between the two values of y, if we call them, that's change in y, change in y, and there is a change between the two values of x. So it's change in x. So that's why we said the slope m is equal to change in y over change in x. So we said the slope m is the change in y, y2 minus y1 to find the difference, and over x2 minus x1. So for 2 points, examples, for 2 points, 2, 5, and -1, 7, okay? The slope m is. So if I have 2 points like this, I can find the slope. Remember, the slope is the change in y over the change in x. And because we know the first coordinate, I mean the coordinates, if you want to put them that way, this is x1, y1, x2, y2. So we can substitute x2, y2 is 7 minus y1 is 5 over x2 is -1 minus x1 is 2. So we end up with 2 over -3. So the slope of the line is -2, 3. So one thing you need to understand about the slope can rise. I mean, the graph rise from left to right if the slope is positive and fall from left to right if the slope is negative. So suppose if you want to verify what we just did, you can do it with that graph and see if the graph would fall from left to right. So first of all, we're gonna graph these 2 points. We have 2 points. Probably we're gonna make them very small. So we have the first point when x is -1, y is 7. So we have 1 point over here, -1, 7. And the second point when y is 2, when x is 2, y is 5. So 2, 5. Now, seeing this point that way, we can conclude that this is your graph when you connect these two dots and you continue indefinitely, as you can see. Well, actually, you can verify the change between the two values of y right there is just 2 to 7 is 5 to 7 is 2. And the change between the two values of x from -1 to 2, you see? -1 to 2, so that's 0, 1, and 2. So that's this one is 3. So that's why, and because it's falls from left to right, we would conclude that the slope is -2 to 3. So I open this parentheses because I know why we're gonna go over many. That's why we said here to calculate the rate of change by finding the slope between any 2 points on the graph. Rate of change is equal slope, and the slope is the change in the values of dependent variable. That means y2 minus y1 over x2 minus x1 because over the independent variables. Now, we said to find the slope of a straight line, look at any 2 points. You can choose any 2 points, right? Any 2 points. So just look because these 2 points goes down here. So that means this would be the change in the independent variable. That means the change between x1 2 and x1. And also, if you look at this one right there, and this one right there, that will be the change between the two values of y. So that's why we said the slope, to make it short, we call it m, is the change in y over change in x, and we call it y2 minus y1 over x2 minus x1. That I strongly advise you to include or add to your notes because we're going to use it a lot. We're gonna come back with more than that because we have a lot of functions. But here, all they ask you to do is really to explain because in these particular examples, they said that the following situations involve a rate of change that is constant, right? Write a statement that describes how one variable varies with respect to the other. Give the rate of change numerically with units and use the rate of change rule to answer the questions. They give you an examples. Every week your fingernails grow 5 inches. How much will your fingernails grow in 2.5 weeks? Well, that's, if 1 week 5 inches, 2.5 weeks would be 2.5 times, right? 2.5 times 5, right? So the length of your nails vary with respect to time. It's over the week, right? With a rate of change 5 millimeters per week. In 2.5 weeks, your fingernails will go 5 times 5 millimeter per week times 2.5 weeks. That would go 12.5. So we can only use the same example. The water depth in a lake decrease at a rate of 2 inches per day because of evaporation. How much does the water depth change in 8 days? 2 per day in 8 days. How much? Yeah, 16, 15 days. 2 per day for 15 days. Yes, 30 because you're gonna multiply it. But we know the water depth, we can say the water, can we say no, I write it not properly. Yeah. The water depth decrease with respect to time, right? The water depth decrease with respect to time at what rate? At a rate of what? Okay, the water depth decrease with respect to time at a rate, we're doing A, right? At a rate of 2 inches per day, right? Of 2 inches per day because of evaporations. I don't know if it's because of evaporations. So the rate of change is negative 2 inches per day, right? In 8 days, I'm gonna do only 8 days. In 8 days, right? You can see in 8 days the water depth decreased by in 8 days negative 2 times 8 would be negative 16 inches, right? Negative 16 inches. Oh no, I don't need to put the negative because we already said decrease. If I said decrease, I don't need to put the negative. Negative 16 inches. So in 8 days. So you understand if I do 30, 15 days, then it's gonna be 30. So that's how you're gonna do all the other ones. Like if you look at B, it says your car maintenance. We can go with your car maintains a constant speed of your car maintain a constant of 63 miles per hour along the highway. How far do you travel in 1.5 hours? So I'm gonna do only one of them. So first of all, your distance travel increase. Look, your distance increase with respect, right? Your distance travel increases increases with respect to time, no? With respect to time at a rate of 63 miles per hour, 63 mph. I can put miles per hour like this along a highway. So how far do you travel in 1.5 hours? So in 1.5 hours, distance is what? Yeah, if you do 63 miles per hour, so distance would be 63 times 1.5. You're gonna find out how long you're gonna do in 1.5 miles per hour. So in this case, it's gonna be 94.5. Remember, I'm not doing both. I only do one for you to see in um, 1.5 hours, you're gonna do 94.5 miles if you do 63. So I let you to enjoy doing 3.8 miles and also the last examples. Now that was just very important to understand, a variables expressing in function of the other one, the dependent and independent variable, what's the meaning for it. Now we're gonna go for the rate of change rule. Um, we said we talked about the rate of change rule because there is so much to learn about the rate of change. So there is a formula that we can definitely use for rate of change. Okay, so that's how we're gonna do it. So the change in the independent variables, very important. Um, the rate of change will allow us to calculate the change in the dependent variables from the change in the dependent variables. So change in the dependent variables, remember, look, if I call, remember, rate of change is equal to slope, right? Now, remember, slope by itself is change. I call it in Y because dependent variable over, yeah, this line is terribly terrible, right? And change in X. Now, because we know slope equal the rate of change, so I can write rate of change equal change in Y is change in the independent variable. Change in Y, I make it shorter, I put Y. Change in X. But remember, if you want to do cross multiply for both sides, you can multiply this one with this and multiply that one with this. It's all depend of what you're looking for. If you're looking for change in Y, one time change in Y give you change in Y or change in dependent variables equal rate of change when you multiply it, rate of change times change in X or change in the independent variable. So that's why we write up there. So that's exactly the same thing I write. Just wanted you to make sure you see it because we're gonna use it later, in this video. So some examples that we can definitely take a look on the following situation. We have a few situations that we can models. We're gonna say that the following situation here can be modeled by linear equations. Remember, linear, that should be a very straight line. In each case, write an equation for the linear equations and use it to answer the given questions. Be sure to clearly identify the independent variables and briefly discuss whether a linear model is reasonable for this situation. Usually I do one or two and I let you enjoy the other ones because my goal is to do one examples for you or two and then for you to practice and make sure you can do the other ones. And then if you get stuck, reach out to me. I'll be happy to schedule an appointment with you so we can go over what you don't understand. So the price of a particular model of a car is $38,000 today and rise with time at a constant rate of $900 per year. So, look, the price of this car, today, okay? You need to write this one. So, price of the car today, price is equal to, or I would say, let P be the price. Let P be the price. Okay, total, let P be the total price. Be the total price. So, okay, look, of the vehicle over the time. Now, the price of a particular model of car is $38,000. And they don't say it's in decrease. They said it rise with the time, at a constant rate of 900. So on top of that $38,000, every year you add 900 to it. So plus 900 after the first year, plus 900 after the second year, plus 900 after the third year, etc. So now we know these functions right here would be 900t. That would be your functions. If it's only the first year, then you're gonna have t equal 1. After two years, is t is 2. After 3 years, t is 3, etc. So we answer the first part of the question. She said the following situation can be modeled by a linear function. That's exactly what we do. You don't have t power something. It's only 1. Write an equation for the following functions and use it to answer the question. So we know here it t is the independent variable, p is the dependent variable, because if t never changed, p would never change. So we would say t independent, p the price dependent, right? So all right. So I'm hoping you get this correct. So the independent variable is time, measures in years. T represent today, right? If equals 0, it represent today. The dependent variables is price. P measures in dollar. So the equations as it says is P equal 38,000 plus 900 T. So the question they ask us to do to answer, how much will a new car of this model cost in 3 years? So remember, what is P at T equal 3.5? Remember, we have the functions already. So we're going to have P would be 38,000 plus 900 times T that I know now, 3.5. Now, using a calculator, after 3.5 years, this vehicle would cost, these vehicles would cost like how much money? It's 41,150 after 3.5 years. So that's how you can model something and do it at any times. If you do D as in dog, you're gonna do the same. Look at D. I try to do A and leave the rest for you, but let me do D also. So you can rent time on the computer. So first of all, you need to review and see what you can. You can rent time on the computer at a local internet cafe for, well, maybe this is no longer possible, but you know what? How about it? We're gonna try it. I'm gonna experiment, maybe not doing it totally, but pay attention to it. You can rent time on the computer at a local internet cafe for a $10 setup charge and an additional $2 for every 5 minutes. Huh. Okay. Now you see, we're not doing it every minute. We do it for every 5 minutes. So if you want to find how much per minute, because if you do it every 5 minutes, it's gonna be more complicated, right? So look, um, we are here. So if you do $2 every 5 minutes, so how much you do every minute? So all you need to do for every minute, so 5 minutes you do $3. Every minute you would do 2 divided by 5. You're gonna do 40 cents, right? So or 40 cents or $0.40 per minute. You can convert and make it per minute instead. So that's exactly what I do for this one. So I do 2 divided by 5 to find how much I pay per minute instead of using 5 minutes. Because if I do 5 minutes, it's gonna be more complicated. So first of all, I would say, um, you can rent. I would say time is dependent variables in minutes. I prefer to use these times in minute. Independent variables is time in minute. Okay, I say dependent variables right? That's the cost, right? Dependent variable is the rental cost, is rental cost in dollar. Now, the equations would be the rental. It all depends what letter I use. I'm gonna use R is the rental for R. Let me call it R. Okay. I'm gonna call it R anyway. So let's call it R. That's would be better to do it that way. Okay. Um, they said you pay a $10 for set of feet. This would never change, but what is variable cost is where you pay 40 cents for each minute. I'm gonna call this T also, right? Independent, this one T. Okay. So this is the functions, the linear model, right? So 10 plus, if you do 5 minutes, then T is 5. If you do 10 minutes, 10, so it all depends. So when they say, how much time can you rent for $25? Now, if what is T if R is 25? So you see, we know everything. So if I do um 25, I'm gonna do 25 equal 10 plus 0.40 t. If I subtract 25 from both, subtract 10 from both sides, it's gonna give me 15 equal 0.40 t. Let's divide both sides by 0.40, so we're gonna end up with 15 over 0.40 equal t. Now, what would be t? Because if you divide 15 by 0.40, t would be 37.5 minutes. Okay, so that's the number of minutes you can do for $25 if you pay $5 for every $2 for every 5 minutes. So it's better you convert down to per minute instead of keeping it for the way it was before. Uh, you know, very important. That's very, very important. Now, let's go with some other things because we have so many to cover in these sections. We still talk about the equations of the line. Do you know all equations for a linear functions? We can talk about so many different ones because we have dependent variables, independent variables, we have initial values. That's what we just did in all of them. So um, dependent variable equal initial value plus rate of change and the dependent variable. That's exactly what we do. Equations of a line in a slope-intercept form. I think we covered that already. This is slope-intercept form where M is the slope and B is the y-intercept. So y-intercept means it's where your graph intersect the coordinates of y, I mean the coordinate at which the graph intersect the y-axis, right? So remember I gave you different formats you can rewrite a function. You can rewrite it as ax plus b. You can rewrite it as y equal mx plus b. M is the slope, b is the y-intercept. Or we can write it ax plus by equals c. That is the general. So in algebra, x commonly used for independent variables and y for the dependent variable. For a straight line, the slope is usually denoted by m, and the initial value or y-intercept is denoted by b. So that's what we're gonna do in many cases. Let's suppose if we have y equal 2x minus 1, the slope is what? The slope is m equal 2, but because y is written in the form of mx plus b. So you can find the slope. You don't need to convert. You don't need to find y2 over y1 or x2 over x1. But if you have something like 2x plus 3y equal 5, first of all, you need to solve by for y. That means you subtract 2x from both sides. So you have 3y equal negative 2x plus 5. If you divide each term by 3, you have y equal negative 2 thirds of x plus 5 over 3. So here, slope is the coefficient of x is, so it's only the coefficient of x when it is written in the form y equal mx plus b. For example, here again, we said the equation y equal 4x minus 4 represent a straight line with a slope 4 because coefficients here is the slope. Remember, this is the slope m equal 4. All right, and y-intercept, okay, so as you see in this one right there. So we have so many examples we can do. Not all the times you're gonna have a slope like they, you have different ways. You either have a positive slope, you so the graph rise from left to right. If this slope is positive, or if this slope is negative, or if this slope is 0, or if this slope doesn't exist. So this is a positive slope rise from left to right. So slope is positive. This is a negative slope. Uh, so it falls from left to right. So if m is 0, if the slope is 0, then you're gonna have something. If the slope doesn't exist, slope does not exist, then it's gonna be a vertical line. So it all depends on what you do. Then you can do it. Varying the intercepts. Remember, intercepts means where you intersect with the axis. So for example, if we have 2x plus 3y equal 5, x-intercept means set y equal to 0. If y equal to 0, 3 times 0 is 0, so we're going to have only 2x equal 5. So for x would be 5 over 2. So that would be your x-intercept. That means you have a value for x, but for y it would be 0. Y-intercept, set x equal to 0 and solve for y. So in a functions like this, if x is 0, 2 times 0 is 0, so we're going to have 3y equal 5. If you divide both sides by 3, you're going to have y equal 5 over 3. So you have a point where x is 0, y is 5 over 3. So intercept means one of your coordinates is 0. One of your coordinates is 0. That's what we call intercept. Okay. Um, that's an example, so I'd like you to see and take your time to it. So we said to create a linear functions from two data points, you let x be the independent variables and y the dependent variables. You find a change in each variable because it between the 2 points. So meaning we know this one is y2 minus y1 over x2 minus x1. So that's mostly what we're planning on doing. Okay, substitute this slope m in the numerical values of x and y if you want to write in the form y equal mx plus b. And you can use the slope and the y-intercept to write an equation in that form. So we can even create our own functions. We're going to conclude because we're going to come back with more functions. We're going to do only one because it said create a linear function that models each of the following situation. Let's do A very quick because as I said, I do one examples and I let you enjoy for the other ones. All right, so let's do it very quick. We said that suppose your dog weighs 5.5 pounds at birth and weighs 200 pounds a year later, right? Based on these two data, points. Find a linear function that describes how weight varies with age. Okay? Remember, your dog was born at something. So if we want to keep W as the weight, okay? So we know the weight at birth was 5.5 pounds. And weight 20 pounds a year later, right? So it all depends on what we want to represent. Do we want to show the pounds per year? Because if W represent the weight of the dogs in pounds and T the times in years, the information given about the weight of the dogs correspond to the point. We have 2 points, right? We can find the slope because when at time zero, remember we said at time zero, what was the weight? 5.5. So that time, that's weight. And after 1 year, what was the weight? 20. So I can use these 2 points. I can use these 2 points to write down my equations. All right. So because I need to find the slope anyway. So because I cannot just go ahead and not doing it. So what I would do in this case, because I have 2 points, because they give me two very important informations, you know, I can write it as um, y, because remember we said we do it with two variables. We're not doing to x and y, but anyway, slope m is changing the y values. What's represent the y's? Because you remember, if you want to see y and x, you can call this one y1 x1 y1 x2 y2. So that means you're gonna have 20 minus 5.5 over 1 minus 0. So doing this, it gives you 14.5. All right. So you know the slope, and at some point, it's very important to know how to write these equations. Remember, for the if you have a point 0, 5.5, that is the y-intercept, and you know a function is written in the form mx plus b. B is the y-intercept, so we can rewrite that functions as y. What is the slope? The slope is 14.5 t plus 5.5. So we write right now the functions. Either I call it y, or if you don't want to call it y, I'm going to call it w. Sorry, I said x. Let me use x instead. Where w is uh, y is the weight in pounds, and x is the time in years. I try to do one example with you here, and then once you use that, you can do another one. But the questions they ask us to find after we write down the equations, y equal 14.5x plus 5.5. When the dog is 5 years old, now at x equal 5, y would be 14.5 times 5 plus 5.5. So y would be at 5 years old. If you substitute, it would be definitely 78 pounds. Now, they also ask you, and at 10 years old, at x equal 10, y would be 14.5 times 10 plus 5.5. So we're gonna have y equal, if you do it for 10 years, then it's gonna be 150.5 pounds. 150.5 pounds. So that's gonna be a big giant dog, right? That's very important to see it this way for it. All right. So we can see it like that and comment on the validity of the models if we want to. We can comment on it. The model is accurate only for lower ages. So you'll see that because after 10 years, it's unbelievable how the dog can be big. But 5 years old, that's okay, you know. Uh, all right. So hopefully you use these to do more examples. In a different video, we're gonna come back for exponential modelings. Hope that's helped. I'll see you in a different video. Take care.